Oh, right. So this question is asking us to do, something. I missed the title. Calculating average and instantaneous reaction rate from a graph of concentration versus time. So average is going to be just over a period of time. So you're just going to look at the difference between the initial starting time and the finish time, and what change in this case, the concentration, if you like, is measured in pressure, right? So atmosphere over the change in seconds. Instantaneous means at that exact moment. So that is where you're going to find that exact spot on the plot and draw a tangent to the curve line to work out what the instantaneous rate of change is going to be. Okay, so let's see what we're being asked then. Is dinitrogen pentoxide being created or destroyed? Well, that's a little bit extreme, isn't it? By the chemical reaction. So is it being consumed or produced? So for this, you are going to look at the shape of the curve. The curve has a negative gradient. That means over the course of time, the concentration is reducing, or the pressure exerted in atmospheres is being reduced. So this means it's a reactant that is being used up. So the dinitrogen pentoxide is being destroyed. Okay, if you saw a positive gradient, that would mean that you have a product that the concentration or partial pressure is increasing of over time. Okay, so we're asked if it's been created or destroyed, what is the rate at which it's being created or destroyed 1,000 seconds after the reaction starts? So that is asking us for an instantaneous rate. So let us find 1,000 seconds on our graph. So this is very small for me. About here, I hope I put that in the right spot. That is the instant at which I am going to draw my tangent. And honestly, this is kind of hard for me to do on the screen, so I'm just going to wing it. I already kind of checked it a little bit earlier. I think, let's see if I can get it in the right place. That's not ideal. I should probably start a little bit lower. And let's try one more attempt, Erin. It's probably about here. Trying to make sure that it looks symmetrical on either side of what I draw. Maybe about here. Okay, so I'm going to look for my X and Y intercepts and go from there. So it's 2,000 and something. What is this? Each one of these is about 100, so it's just over 2,200. I don't know, 2,230, something like that. Seconds? I don't know. I'm just going with what I think it is approximately. Two things, two something, right? 1, 2, maybe it's a little bit less than that. I don't know. Let's go for 25. Close enough, okay? This isn't going to be like exactly what ALEKS would have come out because I can't measure it very well using the tools I've got on the screen because I'm not using the fancy ALEKS one. So and then it's 1.5 something on the top, 1.510, maybe 1.51 atmospheres along the top. That's my best guess. I may be a little bit off, okay? So then to work out my gradient, and remember it's going to come out as a negative gradient because look at the shape of it, right? So I'm going to do the change in y over the change in x, rise over run if you like. So my gradient m is my change in y over my change in x. I'm going to have to find my drawing a line thing here. Okay, so this is just going off of what I can eyeball here. It may not be 100% perfect, but you get the idea. Dun, 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 dun. So that is going to be y, the change in y. So we always do final minus initial, right? So my change in y is going to be 0 minus whatever I read off, which was 1.51 atmospheres, divided by my final 2,225 seconds minus 0. So I'm going to get my gradient in atmospheres per second. It's going to come out as negative. We can't really define a rate as negative. We're just going to acknowledge that it is a rate of consumption. So that, it's going to come out as negative, but we're going to take the modulus of that if you like. Come on, calculator. So 1.51 divided by 2,225 is about 0.00068. So that's like 6.8 times 10 to the power of negative 4, and that is going to be units of atmospheres per second, or atmosphere second to the -1, whichever you prefer. All right, so that is my instantaneous rate sorted. So it's asking me the average rate during the first 1,000 seconds. So to contrast, hopefully I can draw this on the same thing and it's not going to be horrendously messy. So that is asking me about a period between 0 and 1,000 seconds where I put my dot. So it's asking me to calculate this gradient, okay? So if it helps you to kind of eyeball, this is the delta y and delta x. So as you can see, we've got a straight line which deviates from the actual curvature of the line. So it's giving me the average rate in change over this time, but it's not going to be as accurate as the instantaneous rate of change. So again, I can do delta y over delta x. So delta y over delta x, I can't be faffing around with drawing triangles. So what is the change in y? We're just going to do the final value of y minus the initial value. I really can't read because I just happened to put it right under there, but I think it's about it's like 0.8 or something. Yeah, it's about 0.8 something, 0.83 maybe. So 0.830, 0, that is pushing it. And then let's see, where does it end up? Uh, where does that end up? 1 point, I guess it's about where that 1.88 is. So let's go with that, I guess. 1.88, and then divide that by on the bottom, 1,000 minus 1, right? 1,000 minus 0 even. So whatever that comes out to be, and that's going to be in atmospheres per second again. Let's get my little liney thing, draw something useful, and ask my calculator to tell me what is up. So that is going to be 0.83. Again, this is going to come out negative because it's a negative gradient, so you're going to take the modulus of that divided by 1,000. It's going to be around 0.001. I got 0.00105 atmospheres per second, and let's see, did it give me sig figs? 2 sig figs, so that's going to be 0.11 atmospheres per second. All right, so there you have it.